All right, good afternoon. Okay, so what happened was during the recording of the last lecture, since you all were not there, I forgot to switch on the audio, and I went on speaking like that entire like that way for the entire lecture without even realizing that the audio was switched off. I'm sorry for that, but again, though I will upload that lecture as well, but let me quickly go through that lecture, what I have explained in that lecture very quickly, before I start with the different types of fuel cells. So in the last lecture, uh, I explained the basic operating principle of a fuel cell. So I'm just repeating myself because I forgot to on the audio. So I'm just going to quickly give you a recap of what we did in the last lecture in first 10-15 minutes. So in order to understand the operating principle of a fuel cell, there are three different components which a fuel cell is made up of. One is anode, the another one is cathode, and the third one is electrolyte. We supply fuel, which is hydrogen, to the anode. Anode is a negative electrode. Cathode is a positive electrode, and electrolyte will help for the ions to flow from the anode to cathode, and it will also it will prevent the electrons to flow through it. Okay, because if the electrons will flow through it, then there will be a short circuiting. So the electrons will travel through the outer path, and that is how the electricity is generated by the fuel cell. So again, we have three parts. It is anode, cathode, and the electrolyte. At the anode, we supply fuel, which is hydrogen. At the cathode, we supply an oxidant, which is oxygen. And the exhaust, which we get from the fuel cell, is H2O plus heat. Okay, so what is a fuel cell? Fuel cell is a galvanic cell in which the chemical energy of fuel is converted directly into electrical energy by means of an electrochemical process. Basically, an electrolyte is necessary to conduct ions from one electron to another, and the fuel is supplied to the anode, whereas the electrons are released from the fuel, with the help of some catalyst, which will speed up the entire reaction. So the chemical reaction in a fuel cell is very similar to the one which takes place in a battery. Okay, but here the basic difference is, as long as you can supply the fuel cell will be able to give you the electricity, which is not the case in battery. Okay, so fuel cell will be able to produce electricity as far as you are able to supply the fuel, which is hydrogen. So the thermodynamic voltage, or as we call it as an open circuit voltage of a fuel cell, it is closely associated with two things. One is energy released, and the another one is the number of electrons which are transferred in the reaction. The energy released by the battery cell or a fuel cell in the reaction is given by the change in the Gibbs free energy, something which we call it as Gibbs free energy. And it is usually expressed in per mole quantity, and the change in the Gibbs free energy is in a chemical reaction is expressed by it is nothing but it is the Gibbs free energy is given by the summation of all the products minus the summation of all the reactants, where Gi and Gj are the free energies in the species of I in the products and J in the reactants. So if if it is a reversible process, the energy released is completely converted into electrical energy. Okay, which is given by the formula delta G, for an reversible process is given by minus N. Minus stands for the work done. Okay, so minus N times F times VR, or it is also given by minus N times F times E dot cell. or E dot cell. Let us call it as E dot cell, where N is the number of electrons which are transferred in the reaction. F is the Faraday's constant, which is having a value of 96,500 coulomb, and VR is the reversible voltage of the cell or electromotive force of the cell, uh, as we call it as E dot cell. So at the standard potential, which is the standard potential is 25 degrees C and 1 atmospheric pressure, the OCV or the open circuit voltage of a battery or a fuel cell can be given by this particular formula. So E dot cell is RT upon NZ or NF or ZF. Again, N and Z are same and they stands for number of electrons, which is natural log or log of K. So we will see what is K. So K is going to be nothing but it is going to be the uh, it is going to be the reactants upon product. Okay. You will understand this when we talk about some equations. So if you see, these are some tables which give you the Gibbs free energy for typical fuel cells. And if you see, it is at standard potential 298K. 298K means 25 degrees C. Okay. And 1 atmospheric pressure is what it means. So if you see, for different substances, we have been given Gibbs free energy for those substances. Similarly, the thermodynamic data for different reactions at the standard potential is given to us. So if you see, if the reaction is something like this, okay, the Gibbs free energy value is minus 237.3. If the reaction is this, the Gibbs free energy value is minus 228. If it is carbon monoxide, the value is this. So basically, for different reactions, you will find that you will get different Gibbs free energy. So that is the energy released. Now, if you see, we can express this. So each and every term, which is this temperature, okay, or K, this Gibbs free energy, and the the electrode potential or the open circuit voltage of a cell has relation in between them. So if you see, if you solve this, if you want to find out the relation between all of them, or if you want to find out the the open circuit voltage, if you want to find out the OCV, this is called as an open circuit voltage of a cell, at any particular, say for example temperature. If you want to find out, it can be given by the formula of E naught cell minus RT upon NF times log of K, where now we understand that since we have these in the unit, we want to understand why this Faraday's constant F is 96,000 500. So we know that 1 mole, it consists of that this is Avogadro's number, and 1 mole of electron is this, it weighs this much, and the charge per 1 electron is given by this 1.6029 times 10 raised to minus 19. And from that, I can calculate by this particular formula, uh, that if you just cross multiply this, I will be able to get, so it is ideally given by the formula N times E. Okay, so if I just cross multiply, I will get this Faraday's constant. So in order to understand this, I had solved one problem here, where we have calculated the cell potential of a galvanic cell, based on the reduction half cell reactions which are given at 25 degrees C. So we have to find out the cell potential at 25 degrees C for a galvanic cell. Galvanic cell is nothing but it consists of a zinc and copper. So it consists of a zinc at anode and copper at cathode. So zinc, the reactions are also given. So if you see from this reaction, we can understand from this reaction, since it is giving up the electrons in the outer circuit, zinc is at the anode, and the electrode potential at the anode is given by minus 0.76. Similarly, these are accepting these two electrons, which is, copper is accepting the two electrons, which is cathode, and the electrode potential for this is given as 0.34. So we know that at anode, we have the oxidation reaction. It means that the at anode is ready to give up electrons. Similarly, cathode is ready to accept the electrons. And this particular formula is also known as the Nernst equation, which is which is used to find Nernst voltage. So Nernst voltage is nothing but this electromotive force or the voltage which we are talking about. Okay, so if this is given to us, how do we calculate the Nernst voltage out of it? So you see that we know that if E dot cell is simply, we can calculate it by the formula E cathode minus E anode. Now this electrode potentials were already given to us, so from that we can calculate the E naught cell. Now, RT upon NF, I know that R is the gas constant. Temperature, since I have to calculate it at 25 degrees C, I will add 273 plus 25. I know F is 96,500, so I will get this value. Similarly, what is this logarithmic of Q? Q is nothing but, the product at, what you can say, the cathode upon the the reactants at the anode. So it is coming from this particular equation. So you see Q is nothing but it is nothing but the oxidants upon reactants. Okay, it is the same thing which we had discussed even here. So so these are the reactants divided by the products. So if we take a log, say for example, log of A by B is nothing but log A minus log B. So that is what this Gi minus Gj means. So the logarithmic of it is reactants upon the product, and it is nothing but the cathode upon the anode. So if we know the values, we can calculate that, and that is what I have done. So I have got the value as 20. So hence, if I substitute, I can calculate the Nernst. This is also called as the Nernst voltage, or Nernst or open circuit voltage at 25 degrees C. Similarly, if I calculate it at 40 degrees C, I just have to change this temperature value. So if you see, so definitely what we see is at 25 degrees C, the open circuit voltage for a fuel cell or a galvanic cell is 1.061. Similarly, at 40 degrees C, that same cell is giving the voltage as 1.059 volt. It means that temperature does have an effect on cell. Our discussion to fuel cell, system characteristics. So system characteristics is nothing but, if you see the fuel cell cannot work alone. So here you see we have this hydrogen storage tank, which is supplying the hydrogen, to the anode, or in the earlier diagram we had called it as fuel. Then we are, supplying the oxidant or air to the cathode, and we have a fuel stack in between. Okay, so in order for this fuel cell to work, we will require so many auxiliaries such as air circulating pump. We will require a coolant circulating pump. If the temperature of the fuel stack goes up, we will have to cool it down. We will require a ventilation fan. We will require a hydrogen circulating pump, and we will require a controller. Now you see, we will also require a DC-DC converter, because the amount of voltage or the amount of electricity which will be produced by the fuel cell, may not be directly used to run the motor, or we might not get enough voltage to run the motor. So that is why we will either different types of DC-DC converter. So either it can be a converter or an inverter. It can be a buck type or a boost type or a buck boost type, depending on the application. So that is what we had written down, that the fuel cell will require auxiliaries, and amongst all these auxiliaries, if you see, the air circulating pump will will use about 10% of the total output energy of the fuel stack. So the most important energy consumption device is air circulating pump in a fuel cell, but that is required as well. So that was the idea which I wanted to give you. Then yeah, we came to a discussion about, now since we know that the type of electrolyte will decide the type of fuel cell. uh, okay, and from that, different types of fuel cells which are possible are proton exchange membrane, alkaline fuel cell, phosphoric acid fuel cell, molten carbonate fuel cell, solid oxide fuel cell, or we also have something which is called as a direct methanol fuel cell. Now this direct methanol fuel cell is the future, where a lot of R&D is going on. And from the fuel cell working, I can say that the anode of the fuel cell is called as the fuel electrode. It has it has a common the fuel oxidation reaction, and it drives the electron to the outer circuit. That is what the anode does. What does the cathode do? Cathode is the oxygen electrode, because oxidant are supplied to the cathode side. It is the common interface for oxygen and electrolyte. It catalyzes the oxidation reduction reaction, as this does the oxidation reaction. This is oxidation reduction reaction, and it receives the electron from the outer circuit. Similarly, electrolyte, it is present between anode and cathode. The function is to transport one of the ionic species involved in the fuel and the oxygen electrode reaction, and it also prevents the conduction of electrons, because that will give rise to the short circuit. So why hydrogen is most suitable? Because hydrogen is it is ideal non-polluting fuel for a fuel cell, because it has highest energy content per unit weight. Then since hydrogen is not a primary fuel, it is derived from various primary fuels such as hydrocarbons, methanol and coal, by means of a fuel processor. Now there are three different ways in which you can store the hydrogen. So one, we can store the hydrogen in the form of compressed hydrogen gas, which is CHG, and it can be compressed to the pressure of 20 to 34.5 in, and it can be stored in fiberglass reinforced aluminum container. Then either it can be a compressed hydrogen gas, or you can chill the hydrogen below its boiling point, which is minus 253 degrees C, and you can convert it into the form of liquid hydrogen, which then can be stored in cryogenic containers. And third way is, we can react the hydrogen with some metals such as magnesium and vanadium to form metal hydrides. So these are the three most popular ways in which you can store the hydrogen. So if you see theoretically, so this table will talk about the energy content of the prominent fuels in a fuel cell. So if you store the hydrogen in the form of compressed hydrogen gas, you get a very high specific energy. Okay, but the energy density is very low. So energy density is watt hour per liter. It means it depends on volume, and since it has a very low energy density, you know if you want to store more energy inside it, the size will be bulky, and since the size is bulky, you will definitely have the safety concerns. Similarly, if you see the liquid hydrogen, again specific energy is comparable to the compressed hydrogen gas. You see, you are getting a very good energy density as well, but the production process which is required, because if you see, you have to do this at a very very low pressure, zero point 0.1 megapascal, and you have to do it at a cryogenic temperature. So the production is expensive, distribution cost is expensive. So, cost wise, this is very expensive. The third type, if you react it with some, metals such as magnesium hydride and vanadium hydride, you see that, you are not getting that much of specific energy, but you are getting some specific energy, but energy density is, very good. So, size will be less, but then it will have some different problems. Similarly, direct methanol, if you are able to convert, direct methanol into hydrogen, then even here, you are getting a good amount of specific energy as well as good amount of energy density. And that is why I am saying a lot of R&D is going on into this particular technology. Similarly, if you are able to extract hydrogen from petrol, it is compared with the fuel, which is petrol. So petrol is having a specific energy of, 12,400 and energy density of 9,100. So you see, if you want to compare it with the fuel which is used in the vehicle, the fuel cell technology should be viable. Okay. And that is what this table wants to tell you everything about. Now, what we are going to focus now on is, we are going to focus on the different types of fuel cells. Okay, types. So the first type of fuel cell which we are going to start about today is, the acid fuel cells. So if you see out of the list, we have something which is called as a phosphoric acid fuel cell, PAFC. Okay, so this is the generalized form, which is, the acid fuel cell, which is called by that. Now, let us see, how this fuel cell works. So if you see the working, let me just paste this diagram. So, this is how the phosphoric acid fuel cell will look like. So you see A stands for, anode, as we have seen in the basic structure. C stands for cathode. The electrolyte, as I told you, the electrolyte will decide the type of fuel cell. So you see there is a phosphoric acid which is used as an electrolyte. So phosphoric acid is used as an electrolyte, and you see there is a flow of electron in the outer circuit. We are supplying hydrogen as a fuel to the anode. We are supplying oxidant, to the cathode, and this is how the reaction is taking place. So let us write down few points about the acidic fuel cell or the acid fuel cells. Now this the acid fuel cell is, characterized by the ionic conduction of, the H2 ions, and it uses, you know platinum alloy as a catalyst for both, anode for this particular fuel cell. Let me just see if I have the electrochemical reaction, is given by, this particular way. So if you see, we know that uh, uh, if you see, anode, we are supplying H2 as a fuel, which is getting converted into the H plus ions, and it is giving up two electrons which are going to flow through the outer circuit. Similarly, we are going to supply oxygen, uh, and these hydrogen ions are going to flow through the internal circuit, and we are going to have four electrons in the output. And if you see, if you add the anode and cathode, and if you add up, we are going to get water. you know this is going to be the exhaust or the output. uh, this is the electrochemical reaction for the phosphoric acid fuel cell. So in the very early stage, or in the very early development stage, many different acids were investigated to be the electrolyte, such as they have used sulfuric acid, they have tried hydrofluoric acid and phosphoric acid. uh, Basically phosphoric acid won this competition. So in between this sulfuric acid, hydrofluoric acid and phosphoric acid, phosphoric acid won because it is very stable at the temperatures of up to 225 C, and it has high conductivity at temperatures above 150 C, as well as it has an efficient rejection of product water and waste heat at operating temperatures. So phosphoric acid is the only acid fuel cell which is ready for applications. So I'm not writing all this, but you just remember these things, and hence I can tell you that the phosphoric acid fuel cell generally operates at 150 to 210 C, and at atmospheric or slightly higher pressures, and they offer the power density of zero point 0.2 to 0.25 watt per centimeter square. uh, the disadvantage, now why we are not using phosphoric acid in vehicles. Now we are talking about fuel cells which are used in vehicles. uh, the disadvantage, let me write down. The major disadvantage is its dependence on noble metal electrocatalyst. Okay, so you see, it will depend on noble metal electrocatalyst, and that does not work in the favor of this phosphoric acid fuel cells. Also, the temperature of operation. Okay, so the second one is temperature of operation. So definitely, if you want to use this phosphoric acid fuel cell in a vehicle, you will require some heater kind of you will require a heater to heat up this up to 150 to 210 C. So again, we are going to utilize some energy out of somewhere in order for this fuel cell to work, and that is why they are not popular. Now let us talk about the second type of fuel cell, which is alkaline fuel cells. So let me check if I have the picture for the alkaline fuel cell. Okay, so this is how the alkaline fuel cell looks like, or the operation looks like. Again, the similar thing we have here. Hydrogen as a fuel is supplied to the anode, air as an oxidant is supplied to the cathode, but here something is different. So you see, so let me also paste the electrochemical reaction, and then we will try to discuss what is happening here. So if you see, so at the anode, you see the exhaust which is there. So there is going to be the hydroxide ion which are going to flow from cathode to anode, and at the anode, they are going to meet up. So if you see at the anode, this hydroxide ion is going to meet up with hydrogen, and you see the exhaust is at the anode side. Okay, and which will give up these two electrons. So, and the cathode, you see oxygen and the hydrogen or the water, which is giving rise to four oxides of hydrogen. Okay, so let me write down. So these are alkaline fuel cells. Okay, so alkaline fuel cell uses hydroxide, potassium hydroxide has been, so you see what is the catalyst, what is the electrolyte here? The electrolyte which is used is KOH. Okay, so potassium hydroxide has been the electrolyte of choice because of its high conductivity of hydroxide ion. Okay, they operate at around 60 to 100 degree Celsius of temperature and atmospheric pressures. So typically, if you compare it with the phosphoric acid fuel cell, alkaline fuel cell is more attractive for EV application because the cost is lower by almost 5 times if you compare it with the phosphoric acid fuel cell. Uh, Also, you know, if you see the temperature range, so it operates less than 100 degrees C. Okay, and uh, so it is more or less, if you compare it with the temperature of the phosphoric acid fuel cell, which was 150 to 210 degrees C, it is, it is quite, we can say that it is achievable. So we can say that these type of the alkaline fuel cell can be utilized in EV applications. So basically, lower working temperature, works in the favor of the alkaline fuel cell. Okay, so that is the whole, idea. Okay, then let us move to the next type, which is the third type. It is, the molten carbonate, fuel cell, also called as MCFC. And let me just, you know, if I check, if I see, if I have the picture, so molten carbonate. Okay, this is how it, looks like, or this is how it functions. Uh, so here, if you see, so again, basic parts are going to remain same. So anode, cathode, electrolyte, they are going to be there, but the materials which are used for anode and cathode are going to be different. So in this molten carbonate fuel cell, we are using nickel, chromium alloy as the anode material, and lithiated nickel oxide as the cathode material, along with molten alkali metal. So molten alkali metals like lithium or potassium or sodium carbonate. Metal carbonate is used as an electrolyte, and that is why the name. Okay, so the name is molten carbonate fuel cell. So molten alkali metal carbonates, so metals like lithium carbonate or potassium carbonate or sodium carbonate is used as an electrolyte, and it is in molten form, and that is why the name molten carbonate fuel cells. So again, if you see the reaction which is happening at the anode and cathode, again the output is going to be water, but the reaction will be slightly different. So what we are interested in is, in all these reactions, we are interested, from the last lecture, we are interested in the number of electrons which are liberated. Okay, so you see 2 and 4. So we are interested in the number of electrons which are liberated. Okay, so if you see, since we are using carbonate as an electrolyte, you will see that there is a carbon dioxide which is formed in the entire process. Uh, so if you see, you have this carbon dioxide which is produced here. So a consequence of these, of using these electrolytes, of these reactions, is that the CO2 should be recycled from anode to cathode. So either what you can do is, in order to recycle this carbon dioxide, you can either burn the anode exhaust with excess air, and then removing the water vapor, or by using a product exchange device, who can separate the carbon dioxide from the anode exhaust. They typically, so if you want to look at it from the temperature perspective, they operate at 600 to 700 degrees C, and the atmospheric pressures, but the temperature is pretty high. Okay, and because of the high temperature operation, the molten carbonate fuel cells are basically not used for electric vehicle. Okay, so that is one drawback, because they work on the temperature, high temperature, that works in the wrong way, for them to be used in the EVs. So I'm not going into the details of it because it is not used in EVs. So we know the reason why. The temperature is main reason. So now let us go to the next type, solid oxide fuel cells. So in solid oxide fuel cells, uh, if you see again, the basic parts are going to remain same. What is going to differ, is the type of electrolyte which is used. So once this idea is clear, operation or working of fuel cell becomes very, very simple. So you always know that there is going to be an anode, there is going to be a cathode. We are going to supply fuel, which is hydrogen, to the anode, oxidant, which is air, to the cathode. What is going to change is the electrolyte. And as I said, the name of the fuel cell is based on the type of electrolyte used. So let me write down what are the type of electrolytes which are used in solid oxide fuel cells. So this is something different which I think we have not studied in autotronics, and that is why uh, I'm focusing on this part here. So I think we had not written down uh, the names of the anode and the cathode and the electrolyte which is used in the fuel cells then. But here we can discuss about it, and the picture will be much more clear. So this SOFC, solid oxide fuel cell. So from the name itself, we can understand that it is an all solid state fuel cell which employs a solid non-porous metal oxide electrolyte to allow the ionic conduction by you know migration of O2 ions through the lattice of crystal, because it is solid state. Okay, so the name of the electrolyte is this. It is tria stabilized zirconia is the electrolyte which is used. Nickel zirconia cermet is used as an anode material, and strontium doped lanthanum magnetite is used as the cathode material. Okay, so since it is the you know yttria stabilized zirconia which is used as an electrolyte, you see that we will have the oxide which is there in this particular reaction. Okay, we see this which is present, and the operating temperature operates at 900 to 1000 degree C. So you see overall this is also a high temperature fuel cell. So basically it will have all the advantages as if you compare it with molten carbonate fuel cells. But since the temperature is high, it has limitations to be used in EVs. So again, not suitable for EV application. So molten carbonate fuel cell, let me also write it down here, not suitable for EV application. because of high temperature. Solid oxide, again, not suitable for EV application. Now let us move to the next type, which is solid polymer fuel cell. Now this was the fuel cell which we had discussed in detail, uh, in our autotronics. It is nothing but proton exchange membrane fuel cell, or solid polymer membrane fuel cell, solid polymer membrane fuel cell. And we also know that why do we call it as proton exchange membrane fuel cell. So let me, as I have done it for all the other, I have the picture. So if you see, this is how it is going to look like. So you see, we understood that the proton exchange membrane. So we are exchanging the proton, which is a positive ion. So we are exchanging the proton through this solid polymer membrane. So it is going to pass from anode to the cathode, and hence the name proton exchange membrane. Why it is called as proton exchange membrane fuel cell. So let me write down the membrane is sandwiched between two platinum, you know it is, okay, let me just remove it, two platinum electro catalyst porous electrodes. So platinum is used as a catalyst, in this polymer electrolyte membrane fuel cell. So, you have to remember that platinum is used as a catalyst here. The reaction, or, you know, uh, the electrochemical reaction which takes place in this particular fuel cell is given by this equation. So, this is the equation. This is the electrochemical reaction which takes place at the anode and the cathode. Uh, Now, this SPFC, or solid polymer fuel cell, it works at lower temperatures than the phosphoric acid fuel cell, then molten carbonate fuel cell, solid oxide fuel cell. So typically it operates at 50 to 100 degree C. Okay, so if you see, hence I can say that it is suitable for EV applications, because it is a low temperature fuel cell. uh, Now, if you see the advantages of this polymer electrolyte membrane fuel cells, why it is favorable for EV application is because its power density is highest amongst, all the types. Okay. Now, what do you mean by power density is highest? So when the power density is high, the size of the fuel cell can be small. Okay. So the hence I can write, hence the size of the fuel cell can be small. So since power density is high, the size can be small. Uh, the second is low temperature operation. Low temperature, operation. Then third, you know, electrolyte is, a solid electrolyte. Uh, so since it is a solid electrolyte, it does not change, move, or vaporize from the cell. Thus, it does not move, change, or vaporize with, from the cell. The fourth advantage is, you see, this entire, from the name itself, we know that it is solid, polymer fuel cell. So in this entire, in this entire fuel cell, if you see, the only liquid which is there is water. And since liquid is only water, there is no possibility of any corrosion. So corrosion resistant, I can say that, because the only liquid which is present here is water. uh, okay, and hence it is corrosion resistance, or any possibility of corrosion is eliminated. Okay. uh, the only disadvantage which it has is it uses platinum as an electrolyte. Okay, so the only disadvantage which this fuel cell has is it uses platinum. Again, platinum is, one, it is expensive. And if we go back, we started with this acidic fuel cell. If you see, the operation is, the temperature is 150 to 210. Again, it is slightly on the higher side. Alkaline fuel cell, suitable for, you know EVs. Again, why? Because the operating temperature is 60 to 100. Okay. And we see that there is a lot of advantages. So rest, if you see, so out of all these, I think only two, out of five, there are only two fuel cells, which are suitable, uh, to be used in EVs. Now let us go to the next type, which is the sixth type, which is the direct methanol, fuel cell. Okay, direct methanol fuel cell. Let me check if I have the picture for, direct methanol. So the advantage here, which which we all can understand, is that instead of converting the methanol or ethanol, into any other form, we can directly use that as a fuel cell, or we can directly use it as a, as a fuel in the fuel cell. So here, this type of fuel cell is not dependent on hydrogen. There is, one difference. So instead of, hydrogen, methanol can be directly used as a fuel for the fuel cell. Okay, and that is why the name direct methanol, fuel cell. So the very important, and why this is becoming popular, or it may become popular, in the coming days, is because methanol is the simplest organic fuel. Methanol is the simplest, you know organic fuel, which is economical, and it is efficient, and it can be produced on the large scale from the fossil fuels such as coal and natural gas. Secondly, it is the most electroactive type of organic fuel. Thirdly, methanol is a liquid fuel. That is one very, very important advantage. Methanol is a liquid fuel, which now, since it is liquid, it can be easily stored, which can be easily stored, distributed, and marketed for EV applications. So in hydrogen, we had all those disadvantages that we will have to either compress the hydrogen, or we can use the hydrogen in liquid form. But here, methanol is a liquid fuel. So the storage distribution becomes very simple. Uh, yeah, so we know that hydrogen suffers from the storage and the distribution perspective. Uh, Here, let us write down, since we are talking about the anode and the cathode and the type of electrolyte. So here, both anode and cathode use, platinum or platinum alloy as electrocatalyst, while the electrolyte can be, it is trifluoromethane sulfonic acid, or it can be the proton exchange membrane. So electrolytes can be of two forms. Either it can be of trifluoromethane sulfonic acid, or it can be proton exchange membrane. So if you see the the working, or if you see the equations which are related to this direct methanol fuel cell, which can be one of the future fuel cells which can be used. If you see, the amount of electrolytes which are free during this process is very, very high. Okay, so here, as I said, this is again relatively immature technology. So as I said, this is again a lot of R&D is going on. So it is immature. It is still in the research and the development stage, because there are many challenges which are posed by using liquid, methanol as the fuel. So, but in the near future, maybe in the coming years, you might see this direct methanol as one of the fuel cells which are utilized or which are used in the fuel cell electric vehicles. So now, if I just want to consolidate all the types of fuel cells into one, if you see this particular table, so you see we started with this was the first one, second one, third one, fourth one, fifth one, and the sixth one is what we discussed. If you see, you know, this can be used for EVs, this can be used for EVs, and even this can be used for EVs. So there are three potential fuel cells which can be used as an application in EVs, which are this solid polymer fuel cells, or direct methanol fuel cells, and alkaline fuel cells. Again, the reason is the temperature, in the temperature range in which they work. Okay, you see the power density, which is provided by these fuel cells. So power density is, as we know, if the power density is high, the size can be less. And you see 0.2 to 0.3, 0.35 to 0.6, 0.04 to 0.23. So which is again, this is still in R&D stage. But you see these two are most, and you see economy wise as well, the cost is 1000 US dollar, 1000 US dollar, 1500 US dollars. But if you see the alkaline, you see $200, this is $200, and these are $200 as well. So comparatively cost wise also, the alkaline and the polymer electrolyte membrane fuel cells are most suitable for EV, as I can say, EV applications. So, if I just want to consolidate everything here, or if I just want to put everything in one picture, this is how I can uh, I can also put it in this particular way. So you see all the fuel cells are here. So SOFC, MCFC, PAFC, AFC, polymer electrolyte membrane, and all that. And you will see that it has an anode, electrolyte, and cathode, supplying fuel to the anode, supplying oxygen to the cathode. And you can also see the temperature range in which they work. The temperature zone in which they work, and you will be able to see which type of electrolyte ion or ion conductivity, as we are talking about, is been done. So if you see in polymer electrolyte membrane, we have the proton exchange. So proton is exchanged from anode to cathode. So you can see the arrows even here, and you can see in all the other, in solid oxide, you see the oxide is moving from cathode to anode. And you can find that the exhaust or H2O is formed at the anode. Even in molten carbonate, H2O is formed at the anode. In alkaline fuel cell, H2O is formed at the anode, whereas in polymer electrolyte, H2O is formed at the cathode. Here also H2O is formed at the cathode, and even here H2O is formed at the cathode. Now you know that we can use one, we can use two, and we can use three in EV applications. So I'm sure this picture will give you a very good what you can say, a sense of understanding about the fuel cell technology. Another picture, again a consolidated. So I'm just winding up the entire discussion here. So again, all the different types of fuel cells in one picture. This is how you can also draw this picture in this particular way. So you see the electron flow, the hydrogen, oxygen which is provided, hydrogen ions which are moving from anode to cathode. Similarly, this is proton exchange membrane, this is direct methanol, this is solid oxide. You see oxygen ions are moving from cathode to anode. Alkaline fuel cell, hydroxide ions are moving from cathode to anode. Molten carbonate fuel cell, carbonate ions are moving from cathode to anode. And in phosphoric acid fuel cell, again hydrogen ions are moving from anode to cathode. So again, this is a summary kind of a thing, which I want to put in front of you. So again, if I want to summarize all the different types of fuel cells, I can also put this particular diagram here, which will again give you the consolidated, what you can see, the consolidated components. What is used as an electrolyte, what is the operating temperature, what is the charge carrier. So what is moving from what, so which ion is moving from anode to cathode or cathode to anode. Okay, whether you require the external reformer, do you want, and reformer is a device which produces hydrogen, so do you require this external reformer? The prime cell components, whether they are carbon based or graphite based or stainless steel based or ceramic based. Catalyst, which particular thing uses platinum as an electrolyte, that you can see. And the heat exchange, So independent cooling medium, or electrolyte calculation. So what kind of heat management system does this fuel cell has? So again, there are a lot of ways in which we can put all these things in a thing. Again, since we have spoken about the Nernst equation, again, this particular, the overall cell reaction. So from the overall cell reaction as well, we can write down the Nernst equation. So that we had written down this equation as E cell is equal to E dot cell minus RT times ZF and log of Q. So it is nothing but the same thing. If you see, this is the overall cell reaction. So if you see, whatever is there on the right hand side is what you see here. So the logarithmic of H2O, and this is how you are able to see that. Okay, so anode cathode, and you see it is the similar form of reaction which we have used. So this is how we can write down the Nernst equation for the fuel cell. So there are a lot of ways. So if you are confused, I can also give you this. So for different types of fuel cells, what are the reactions which are happening at the anode, what are the reactions which are happening at the cathode, and you can point out how many electrons are released, and from that you can calculate the open circuit voltage for that particular fuel cell. So there are different ways or different tables which I can present in front of you, uh, just so that I can tell you how these fuel cells can be utilized in EVs. So again, please try to understand here that fuel cells are the device which can be used in conjunction with the battery technology. So we know that we are using fuel cell in conjunction with the battery technology because there are certain drawbacks of the fuel cell technology. So if you want to see a typical configuration of a fuel cell hybrid drivetrain. So let me write down a typical configuration of fuel cell electric or hybrid drivetrain. So it will look something like this. So if you see in this particular uh, you know picture, that we are taking input from accelerator pedal. So this is the input, this is accelerator pedal, brake pedal. Then we have the vehicle controller. So you see we have the fuel cell system, and we have this peaking power source. Then we have this electronic interference, we have the motor controller here, we have the motor, electric motor controller. Okay, then we have this is electric motor or traction motor as we know as. Then we have the transmission, we have wheels, and you see there are different the command signals which are sent from one system to another, which can be used to overall design the entire fuel cell system, or in order to design the fuel cell vehicle. So basically there are different control strategies which can be used in fuel cells, as we are using in a typical hybrid drivetrain. So either it can be a peaking power source, the power output, so it depends which type of control strategy you are utilizing for a particular fuel cell. But this is how we can say that these are the different types of fuel cells which can be used. And also at the very end of this particular topic, let me also see if I can compare all the types, here in front of you. So just give me a minute. Let me just see if I have that, comparison chart, which will be easier for you to understand. Uh, you know, so okay, so this is one such thing which I have. So if you see, this will give you a very, very realistic idea about all the three technologies. So you see, we spoke about hybrids, we spoke about the battery electric vehicles, we spoke about the fuel cell electric vehicles. So you see, what is the propulsion unit? In battery electric vehicles, it is pure electric motor drives. In hybrid, it is electric motor plus IC engine. In fuel cell, again, it is a pure electric motor drive, and that is why they are called as fuel cell electric vehicles. Energy system here, in battery electric vehicle, it can be either a battery and a combination of battery and an ultra capacitor. In hybrids, it can be a combination of battery, ultra capacitor, and IC engine. In fuel cell, it can be a fuel cell, which is where the fuel is hydrogen, which is producing the electricity. It will need battery or ultra capacitor to enhance the power density for starting, because initially we know that the power density is low. Then the energy source and the infrastructure. So in battery electric vehicle, the energy source is we are charging the battery from the grid. Here you see the energy source is either the gasoline station, because we are using IC engines, or it can be an electric grid charging facility for plug-in hybrids. So for a fuel cell, you can the energy source can be either hydrogen, or it can be a hydrogen production and transportation infrastructure. So either you can use reformer, or you can produce hydrogen on board and you can use that hydrogen. So what are the characteristics? The characteristics of the battery electric vehicle is that it is a zero emission vehicle. It has a high energy efficiency. You can get independence of crude oils. So you are independent from using the crude oils or fossil fuels. The characteristic is they can be used for shorter range. They have a high initial cost. They are commercially available. Here, hybrids, they have very low emissions, high fuel economy as compared to IC engine vehicles. They have longer driving range because of adding this electric motor. They have dependence on crude oil, high cost as compared with IC engine, the increase in fuel economy and reduce in emission depending on the power level of motor, and they are also commercially available. Whereas in fuel cell, they are zero emission, ultra low emission vehicle, as we call it as. They have high energy efficiency, again, independence from crude oil, satisfied driving range, because in one once we store the hydrogen on board, we can get range of up to 900, 800 to 900 kilometers. The cost is very high, but the technology is still under development. And what are the major issues in battery electric vehicle? We have battery and battery management issues. We know we have something which is called as thermal runaways. If we don't check the battery temperature, then charging facilities which are not yet developed, and the cost is the downside. Here issues is multiple energy sources, and since there are multiple energy sources, the control of them, the optimization and the management of all of them, and the battery sizing and the management. So you see, this is a lot more complicated. And here the cost, the cycle life, and the reliability, and you see the overall hydrogen infrastructure. So if you see, in India, still the technology is under development, but even in US, they have 40 odd hydrogen stations, where they can go and fill up the hydrogen across entire US. As per the last data, I don't remember the year, but I think 2017 or 18 data, they are having not more than 40 compressed hydrogen gas stations. So you see, the infrastructure is the major problem here. So if someone tells you to summarize all these things which you have studied, so we can do that in in a very simple way. So again, I have different such tables to present in front of you. I'm going to paste, all of them for your reference, uh, so that, you know, you can just go through all these tables just to understand, because, we have covered majority of these, almost all the things we have covered. So the only thing is, if someone tells you to summarize the, plug-in hybrids, battery electric, hybrid electric vehicles, you should have a ready-made comparison charts with you. So that is the whole, idea of, having these charts, with us. So, I can explain all these charts as well. So, let us go back and see. So again, this is the same thing, so I'm not going into this. Again, if you see, if you want to compare the hybrid electric vehicle with plug-in hybrid electric vehicle, a battery electric vehicle, and a fuel cell electric vehicle, so you see the size of battery. In hybrid, the size of battery is around 1 to 2 kilowatt. In plug-in hybrid, it is 5 to 10. In battery, you see the size, it is up to 100 kilowatt. Again, in fuel cell, it is similar to an hybrid electric. So driving with nearly empty battery is possible in fuel cell because we have a backup of IC engine. In plug-in hybrid, again, it is possible. With nearly empty battery in battery electric vehicle, it is not possible. In fuel cell electric vehicle, it is possible because you are producing, as long as you are able to supply the fuel, which is hydrogen, your vehicle can work. So driving range with full tank, for a hybrid electric vehicle, you see the range is 700 kilometers. In plug-in hybrid, it is 30 to 100 kilometer battery driving range, and 400 to 700 kilometers on fossil fuel. uh, you see, for a battery electric vehicle, it is maximum, it is 400 kilometers depending on the battery size. And you see fuel cell, again, it is 400 to 700. So it is comparable with, the hybrid electric vehicle and also the IC engine. So charging and fueling, refilling, so battery charging only during driving, refill the fuel tank from fuel station. So, you can just go through, all these things. So we know that these are emission and zero emission vehicles. Again, so driving range for IC engine, it is high, battery electric vehicle low, hybrid electric medium, and plug-in hybrid, it is high. Efficiency, IC engine, we know that it is having a low efficiency. Battery electric vehicle has high efficiency. Hybrid, again, low. Plug-in hybrid, high. Fuel type, gasoline, we know it is electric, gasoline plus electric, gasoline plus electric. Overall cost is very high. uh, Actually, this should be the opposite. It is low, and this is high, and this is medium. So structure, it is simple, but plug-in hybrid, it is complex. The advantage, it is mature technology, battery performance, simple and reliable, and it is commercialized. It is pollution free, if it is efficient, low emission, high fuel economy, reliable and durable. And harmful emissions, poor fuel economy, recharge time is high, bulky, and more number of components. Energy storage, we have fuel tank, battery, and ultra capacitor. So basically, to summarize, I'm sure by the end of, uh, this, we can say that we have thoroughly, we have seen all these three, technologies, and at least now we have a better understanding of, all this technology. So again, what are the pros and cons of hybrid car? I'm just putting these slides so that, you are able to understand it. So basically, if you see right from the beginning, so we started with hybrid vehicles. Before that, we saw the performance of IC engine vehicles. Then, we came to hybrid electric vehicles. We understood the different types of hybrids, how they work, how they operate. And, we also saw, how the electric vehicle operates, what are the different configurations, what are the different traction motor types, what are different types of batteries which are used in electric vehicles. Similarly, for fuel cells, what are the different types of fuel cells, which of them can be used in EVs. And then at the end, we have compared all the three technology side by side, so that now, at least at the end of this syllabus, we are clear about, all these three technologies. So I think we have covered the entire syllabus.